Then the explanatory variable in an experiment are called factors. Okay, we used explanatory variable for x in linear regression. Here, they are called factors.
Okay.
Many experiments study the joint effects of several factors. In such an experiment, each treatment is formed by combining a specific value called a level of each of the factors. So factors are the variables that cause the response. Like for example, suppose temperature is a factor, suppose. Then different levels of temperature can be used, like 60 degrees Celsius, 80 degrees Celsius, 90 degrees Celsius. These are levels of the factor. The factor is temperature, and factors may have different levels.
Okay. Got it.
In the last class, we saw that a strong association need not mean causation. We cannot infer causation from a strong association. I gave you an example for that, one with two fertilizers.
Yeah.
So we can only infer causation from an experiment, a controlled experiment. In principle, experiments can give good evidence for causation.
Right.
Okay, and then the placebo effect.
The what effect?
Yeah, type of placebo effect.
Oh,
So
placebo. Okay.
yeah, so in medical treatments, it is observed that when people know that they are being treated, they tend to respond positively. So it may not be it might not be that the given pill is good. It may be that the people are responding positively. It may be due to the placebo effect. So when you test a pill, we have to form two groups. For example, suppose you have a pill for headache. Okay,
Yeah.
you have 100 subjects, 100 people. You give the pill to 100 people and measure their responses. Suppose after a certain period of time, they say that their headaches are fewer. Okay, so can we conclude that the pill is better? No, the responses that we saw may have been due to the placebo effect. People tend to respond positively when they know they are being treated.
Oh, okay. So it's practically like psychologically.
Yes. So what we do is we give a placebo. Placebo is a dummy treatment. It looks just like the pill, but people don't know the difference, and placebo has no effect actually. So what we do is we redesign the experiment. Divide the 100 people into two groups. To one group, give the pill randomly. To another group, give a placebo. Okay, and now measure the responses. If the pill shows more good response in the subjects than the placebo, then the pill is actually good. But if they both show the same proportion of positive effects, then there is no difference. The pill is not good. So this type of experiment is called a comparative experiment. We compare the effect of the pill with a dummy or any other treatment. So this is a comparative experiment. And when you do medical tests, simulate experiments for medical tests, you have to take a placebo. if you treat, if you have one treatment, you should compare it to a placebo.
Okay.
And this group to which we applied the placebo is called the control group.
Okay.
Okay. So by a design of an experiment, we mean the layout of the treatments, how the subjects should be selected, how to apply the treatments, how to select the treatments, and all. Okay, and how to measure the responses and compare. All
Right.
these are meant when we say a design of an experiment. So
Okay.
in this section, we will learn how to design experiments, good experiments. Randomization is one important key for the design of experiments. So in this example, do not just apply the pill to any group. Like you divided the group into 50 each, two groups of 50 each. Use randomization to do that. If a doctor divides the 100 people into two groups according to his opinion may be biased. He may put maybe 50 people in who have severe cases of headache.
Yeah, that's true.
So that will be biased. So what we do is randomly select from the 100, 50 people and form group 1. The other 50 people will form group 2. And then randomly assign one of the treatments to one of the groups. So this is called a completely randomized experiment. We chose the subjects by randomization and we apply the treatments by randomization. By randomization, we mean we use probability or chance to select the treatments or subjects. Okay, so these are the keys of an experimental design. And the first one is compare. Compare two or more treatments. This will control the effects of lurking variables on the response. For medical tests, placebo effect is a lurking variable. There could be other lurking variables. So depending upon that, we should control the treatments. You'll see how to control treatments. You'll be using blocking as one of the methods. And then randomization. Use impersonal chance or probability to assign experimental units to treatments. Then repeat. Repeat each treatment on many units to reduce chance variation in the results. Like if you apply it to very few people, like if you give a pill to say maybe 4 people and a placebo to another 4 people, and if you observe good results for the pill, that doesn't mean that the pill is good. You only applied it to 4 people, so the positive response may have been due to chance too. So we should apply to large people, large group, as far as possible. Statistical significance. An observed effect so large that it would rarely occur by chance is called statistically significant. So we are sure that it doesn't occur by chance. It rarely occurs by chance. So that's called statistically significant. If you apply the pill to 4 or 5 people, the result may not be statistically significant. But if you apply it to 50 or 100 people and see good results, then that means it cannot have been due to chance. So it is statistically significant.
Okay, that makes sense.
Then how to randomize? So to randomly select a group, we follow this method. Uh, Assign digits to, or make a list of all the people from which you want to select a group. Okay, and assign digits to numerical values to each person or experimental unit. Then use a calculator or a random digits table given in the book and randomly select the group. I'll show you an example. Okay, so here doctors identify chronic tension type headaches as headaches that occur almost daily for at least 6 months. Can antidepressant medications or stress management training reduce the number and severity of these headaches? Are both together more effective than either alone? Investigators compare 4 treatments: antidepressant alone, placebo alone, antidepressant plus stress management, and placebo plus stress management. Outline the design of the experiment. The headache sufferers named below have agreed to participate in the study. Use table B at line 151 to randomly assign the subjects to treatments. So here what we do is first label the subjects. So this one we can label as 01, this one 02, 03, 04, 05. Hold on one second. Let me see if I can make it larger. Okay. Okay. And then what we do is we assigned labels to all the individuals. Now,
Okay.
do you have your textbook with you now?
Yeah, I can. Grab it. Okay.
Yeah, or the last page. It's given on mine. It's on the last page. You have to look at the random digits table.
Random digits. Okay.
Yes. In it, we will enter line 151. Actually, we can enter any line. This is a one log sequence of random digits. They are just given as rows or groups of 5, and each row is named as a line, but it is actually one single sequence of random digits generated by a computer. Okay. So we can enter any line, but here textbook specifically says to enter line 151. So we'll enter there. What's the
But
first
there's no. I don't. Oh,
on the next
there's no
page?
151. It ends at 150.
Next page. Don't you have it?
No.
Oh, hold on. I'll post it. I'll try to post it here. Hang on. I'll post part of it here.
Okay.
Then that's the line that shows line 151.
Oh, I don't know why mine. Because mine at the back of the page it shows tail probability and stuff.
Are you looking at table B, random
Yeah, it will
digits?
be random digits.
And one page goes till 150, and on the next page it starts at 151.
Oh, the back of the page is T distribution critical values table D. I think this missed a page like the book because I don't see a table C.
Oh, I think, yeah, it missed a page. Yeah. Okay, we'll use this. So we'll enter in this line 151 and start reading of 2 digits. Okay, first one is 03. Okay, so we pick the name corresponding to 03.
Is
There's what, and next one is 80. We don't have anyone named 80, so we'll skip that. Then 22. Okay, 22
okay.
here. So
Is me.
yeah.
Then 93 isn't there. 30.
Hold on. And there are four about around. There are 4 treatments here to be applied. So
Okay.
it should have a group of 9. We won't choose all the groups. We'll just choose one group just to show you the method. So 22 is me, and then 93, 41, 29. So that is shoe. And then 26, Paul. Then 48, 01. If we get any repetitions, we won't select it because we have already selected that person. 98 is not there. 12, Hatfield.
Hatfield.
Then
There's no
37,
37.
11.
There's a
So,
Buha.
yes. Then 11, 31.
30
So 31,
towns.
yes. Math.
I guess it'd be easier to write out the numbers first, right?
Yes. So we have 9. This is group 1, right?
Yeah.
This is group 1. And similarly, we take 3 other groups. Okay. Actually, we just need to take 2 more groups. The rest of the 9 will form the 4th group.
All right. That's true.
Okay. That's how we use random digits table to select a group. This is completely chosen by random because these numbers are randomly given by output by a computer. So all numbers have equal chance of being there.
Okay.
And you can also use a calculator to do the same thing. So you have to go to, you're using, we'll look at that later, TI-89 keystrokes for random digits. Okay. And here also it says outline the design of the experiment. I'll show you that. So I'll write a flow chart. So first there is a random allocation. We divide it into 4 groups.
Okay.
Group 1, 9 subjects. Group 2, 9 subjects. Group 3, 9 subjects. Yeah, and then these groups are selected by random. Okay, and then we will apply. There are 4 treatments here in this problem. We'll apply 1 treatment each to one of the groups randomly. So the first treatment is antidepressant alone. It's written there. Antidepressant alone,
Yeah.
underline then. Placebo alone, antidepressant
And
plus stress management, and placebo plus stress management. So then, yeah. Treatment 1, antidepressant. Then treatment 2, placebo. Treatment 3, antidepressant plus stress management. Antidepressant plus stress management. Treatment 4, placebo plus stress management.
yeah.
So we assign treatments and then we measure the responses.
Okay.
The measured responses severity of headache and number and severity of headache. That's what we measure.
Yeah.
Compare number so this is the outline of the design of the experiment. Okay, we have to write a flow chart like this to show the outline of the experiment.
Okay.
Alright, you save the page.
Okay. So the results would be given to us, right?
Yes. Here you will just design it. You won't actually carry out the test here.
Because you're just doing the experiment in this, like the procedure of it.
Yes. We are just outlining it here. We are just learning how to design experiments correctly.
Right.
Shall I erase the page?
Yeah.
And then double blind experiments. Neither the subjects themselves nor those who work with them know which treatment any subject had received. That's double blind. So some experiments.
Isn't that just to ensure
Can you repeat it?
there's no bias or anything
Yes.
going on?
Yes, sometimes we need the experiments to be double blind so that
Right.
the personnel doesn't choose, like, shouldn't know which treatment each person is getting. So that if personnel and subjects don't know it, it's double blind. If only the personnel don't know which treatment each subject received, it's single blind.
Okay.
And there's the matched pairs design. Hold on.
Okay.
So when we compare two experiments, two treatments, it's called a matched pairs design.
Okay.
So all the subjects or experimental units must take both the treatments, and then we compare the effect of the treatments based on all the units. For example, Suppose you want to know the effectiveness of an SAT coaching class. So suppose you have 50 students,
Okay.
and you give them an SAT practice SAT test first and record their scores, and then you give them the coaching class, say a 2-week coaching class, to all the same all 50 students, and then you give another test to the same students and record their scores.
Okay.
So the same students took you have two scores, so one for before the coaching and one after. So you can compare the effects of before and after scores for all the same students. So all the students took both the treatments, before and after. So this is called a matched pairs design. We can compare two treatments if all the subjects or units take both the treatments.
Isn't that just like all of the subjects are taking the same treatment at both times anyways?
Yes. So if different subjects took it, we cannot compare the treatments effectively. So that's not a matched pairs design.
Okay, I get it. So you're comparing the effects of the same subjects. Like if the subjects in the beginning had taken the first treatment, and then the second subjects take the treatment afterwards, then you're comparing the two results then.
Yes. But in some problem experiments, we have to give the treatments to two different groups. But if they are given to the same group, both the treatments, it's a matched pairs design.
Okay.
Then we have the block design. So a block is a group of experimental units or subjects that are known before the experiment to be similar in some way that is expected to affect the response to the treatments. In a block design, the random assignment of units to treatments is carried out separately within each block. So what we do is we first study the treatments. And suppose beforehand, before you do the experiment, you know that certain group of treatments will have the same effect. Then we group them together and call it a block.
Okay.
So I'll use. Go ahead.
Predicting the results and then grouping them accordingly?
Yes. Remember the fertilizer example that I showed you before? I'll just take 4 plants.
Yeah.
You have 2 fertilizers. If you assign fertilizer A to 2 plants randomly and fertilizer B to another 2 plants randomly, and then look at the results, it may not be a good experiment because soil condition is a lurking variable. So what we do is first study the soil condition. Okay. Suppose we see that these 2 plants have the same soil condition, and these 2 plants have the same soil condition. Okay. So these are blocks. This is first block. This is the second block. Within each block, there are experimental units that are similar in some way. That will affect the response. That's given here. A block is a group of experimental units or subjects that are known before the experiment to be similar in some way that is expected to affect the response to the treatment. So the plants in this group will behave in the same way, will have almost the same growth, right? Because they have the same soil condition. And these 2 plants have the same soil, another same soil condition. So these are 2 blocks. Now we can apply the treatments within each block. Say randomly assign A to that plant and B here, and maybe A here and B here. Okay. So we apply both the treatments within each block. So that said here, in a block design, the random assignment of units to treatments is carried out separately within each block. Okay. So now we can compare A and B. Now, if A causes still causes more growth in both the blocks, then A is a better fertilizer, right? Because we have eliminated the lurking variable, which is soil condition.
Right.
That lurking variable is eliminated because both these plants have the same soil condition. We can compare them. So this is called blocking. In blocking, we group similar experimental units of subjects together.
Okay.
So another example of block design.
Okay. So this is how they're separated and grouped.
Yes. The progress of a type of cancer differs in women and men. A clinical experiment to compare three therapies for this cancer therefore treats sex as a blocking variable. Two separate randomizations are done, one assigning the female subjects to the treatments and the other assigning the male subjects, because it's known beforehand that males and females differ in the progress of the type of cancer. Okay, so they're divided into men and women. Here, one block is men. All the men form one block. Women form another block, because it is known beforehand that men and women differ in the responses. Okay.
Right.
So figure 3.6 outlines the design of this experiment. Note that there is no randomization involved in making up the blocks. They are groups of subjects who differ in some way. Sex in this case, that is apparent before the experiment begins. We didn't separate men and women by randomization. We separated it because we knew beforehand that they differ in the response. So two groups and then randomly assign the treatments. All the three treatments are applied to both the groups, both the blocks. Okay. Then men are divided randomly into three groups. To each group, we randomly assign one of the treatments. And women are randomly divided into three groups. One treatment is applied randomly, and we compare the survival rate for women separately and for men separately. Okay.
Okay.
We won't compare the survival rates of men and women because they differ in the responses. Okay.
Okay.
This is another example of block design. Okay. Yeah, that is that section. Now, yeah, we'll do some problems.
Okay. So wouldn't the problems in this section just be different ways of grouping?
Yes. Just related to experiments, how to select groups and how to apply treatments, the problems that may occur. So explain what is deficient in each of the following proposed experiments and explain how you would improve the experiment. Two forms of a lab exercise are to be compared. There are 10 rows in the classroom. Students who sit in the first 5 rows of the class are given the first form, and students who sit in the last 5 rows are given the second form.
Okay. How I would improve the
Yes, here
experiment.
it is not done randomly. The treatments are
Oh,
not applied randomly.
that's
So,
true.
so we have 10 rows in the classroom. So we choose 5 rows
You
at
should,
random, or and then apply to,
yeah,
or we can pull in all the names of the students in the classroom.
and then randomly choose the half the amount of students to
Yes,
be one form and half the amount to be the other form.
yes. And B, the effectiveness of a leadership program for the high school students is evaluated by examining the change in scores on a standardized test of leadership skills.
Okay. Um, so there isn't any difference in the test given.
Like,
Like there could be two different tests to test the leadership skills.
no, we should compare it to an empty program, like what it would be for students who did not take the leadership program and
Okay.
who score here they said change in scores in standardized tests. That means 2 tests were given, one before the leadership program and one after the leadership program. Maybe the students did better because they took the first test and had some experience on how to take the test. Maybe they did better because of that and not because of the leadership program.
Right. Okay. So then,
Yeah, you try C.
an innovative method for teaching inductive algebra. Okay, but then it's okay. So it's with two different courses, like the zoology and the botany course.
Yes, so we cannot
And
compare the effects. Yeah,
yeah, because it's not like testing on the
the same
same people.
students. Yes, they should have tested this new method for the first semester for the same set of students, and without the new method for another semester for the same set of students. Then we can
Yeah.
compare the effect. Okay.
Yes.
So for the first one, ability to grow in shade may help pines in the dry forests of Arizona resist drought. How well do these pines grow in shade? Investigators planted pine seedlings in a greenhouse in either full light or light reduced to 5% of normal by shade cloth. At the end of the study, they dried the young trees and weighed them. Okay. So First, the experimental units of subjects. We call subjects only human beings. So here, experimental units are the pine seedlings in the greenhouse.
Right. And then the oh, should I write it down?
This problem I'll show you.
Okay.
Okay, and then the factors. The factor is light,
Yeah.
and light has two different treatments. We apply two different treatments here. So the treatments are full light, then reduced light, reduced.
5%. Yeah.
Okay. Then a response variable. What's a response variable that we measure?
The
weight. Okay, you do this one.
okay. So how can we reduce the rate of abusers? Telephone surveys. Okay. So the experimental unit is whether the interviewer. Okay, I'll write it down.
The experimental unit are the objects on which the treatments are applied.
Oh.
Or if they are people, we call them subjects on which treatment. So here,
or like the people being called.
Yes.
Oh, this is what I was talking about. Whether
fact is just the introductory remark.
I thought it. Okay.
Yeah, it has treatments. The treatments are the specific ones.
Okay.
That's not the treatment. The treatments are the here introductory remark is the factor. To check that, we will be applying different treatments. What are the treatments applied? The introductory remarks are the interviewer gave her name. That's one treatment. Gave her name. In others, she identified the university she was representing. That's the second treatment. And then still others, she identified both. So 3 treatments are there.
This
responses,
interview
how many
is the
surveys were
interviews.
completed. Okay. Okay.
Okay. Experimental unit. Okay, do I keep?
Yeah, the 22,000 male physicians. Those are the treatments. Factors just aspirin, whether aspirin reduces heart attack. And treatments are the specific combinations of the factors. So
Okay.
treatments are aspirin and placebo.
Okay, 1 second. Okay, 1 second.
Okay, sure.
The aspirin. So the
Yes,
factor is
treatment.
whether the aspirin.
Yes, treatment is what we are suspecting will cause the response. We are checking whether we are guessing or checking whether the aspirin will decrease heart attacks. So the factor is aspirin. We are not checking whether the placebo will decrease heart attack. We are just checking whether the aspirin decreases heart attack. But in to do that, we should actually also apply the placebo. So treatments are aspirin and placebo.
Okay.
Response is the number of
Is
heart attacks. And we try to draw a diagram like I did. Start by a random allocation, then divide them into two groups. Group 1, 11,000 physicians. Group 2, 11,000 physicians. Then to one group apply aspirin, to another group apply placebo. Then compare the responses.
okay. I can say subjects or physicians.
You can start by saying random allocation, and then
Okay. I'll do it at the bottom. And then I can
divide into two groups. Yeah.
then the 11,000.
Yes.
11,000
Yes.
physicians with the aspirin.
Now you'll indicate the treatment later. This is group 1.
Oh, okay.
Group 1. This is group 2, 11,000. Then you'll apply the treatments. To one you will assign an aspirin randomly, and to another placebo. And then you will compare the number of heart attacks.
Okay.
Okay. And then see what does it mean to say that the aspirin group had significantly fewer heart attacks. It means that the number of
Aspirin
less
actually
heart
worked.
yes, the number of less heart attacks that we found in aspirin group was not caused due to chance. That's
Right.
what we mean by significantly fewer heart attacks. Okay. Alright, you save the page.
Okay. Okay, I saved it.
Okay, alright then. Bye.
Okay, thank you. Bye-bye.